Okay. Well, the next lecture, that's also on porosity and moisture fixation, but this time characterization. And there might be some of you who have already used the techniques and would like to supplement, and you're very welcome. So let's start. What to bring home? You won't forget this, will you? That we have this variation in porosity and the definition vary. That the pore structure of cement paste is affected by the drying and heating if we treat it. So conditioning, preparing your samples before you actually look at the pore structure may alter the pore structure. And that has to be considered. Several methods of characterization of porosity and water fixation exist. And when you select the method, you should consider the property you want to investigate. What is it you need information on? Is it total porosity? Is it porosity in a given size range? Or is it the behavior of the water? What are you going to use this data for? The size range you want to investigate, and possible effect of sample preparation. So let's start. The motivation effect of conditioning. I'll start with that because that will give some background in comments to the methods. Characterization of porosity, the central and the summary, and the references. So motivation. As before, we are interested in information on understanding of porosity, moisture fixation, and the state of water in materials because it has an impact on engineering properties. Both the porosity, the strength, and the durability, and when we're talking about moisture fixation and the state of water, it's the creep and shrinkage, volume, stability of the material, and transport of substances, durability issues. And most of the durability or deterioration mechanisms, they are linked to water. If we have a low amount of water, if we have a low relative humidity in the material, the degradation processes will take place at a very low rate or not at all. So it's relevant. And please remember, when you're talking about materials, they are to be used in a structure. And it's the performance in the structure which is the final consideration of the user. And the state of water, it depends on the porosity. When we're talking about cementitious materials, concrete or mortar or cement paste, we have to consider the range we're looking at. And concrete is a composite material at different levels also. We have the centimeter scale. Here we have split cylinders of concrete, and they have hydrated either. They're very young, where we see that the fracture has taken place in the paste. You can nearly see no aggregates here. And then 3 days old, where we see that the paste has become stronger, and we have also fracture in the aggregates. You see the red and black aggregates here, white. Then we could also look at the concrete at a different scale, the millimeter scale, and this is what, for instance, we see in the fluorescent or the impregnated thin sections, which can be quite useful to get an overview of the structure. And finally, we could go deeper into the structure and look at the microstructure, for instance, with a scanning electron microscope. We could also use transmission electron microscope, where we can get at the nano level, and that's what you saw some of the micrographs which Karen Scribner showed on Monday. Again, remember when you read the literature that the definitions vary. So, the conditioning. If you take a sample, a concrete for instance, and you look at the shrinkage, the drying shrinkage. Initially you mix it and it cures, and at a certain time you will expose it to some environment, and often it's not a wet environment, totally wet. So you have some drying, and here we have the shrinkage in percentage as a function of the total porosity. And what you see here, initially, we have a shrinkage called here the first shrinkage. Then if we wet the sample, we will have swelling and expansion of the material. But we also see that there is some of the volume change which is not recovered, some reversible shrinkage. There seems to be a change in the structure of the material. And if you look here, another graph where we have the shrinkage, downwards and upwards swelling, increase in volume, and as a function of time. And then we have some samples which have been exposed differently. We have here the blue one, drying, and then exposed to wetting, drying, wetting, and you get these volume changes. Or if you store the sample in water, you actually have a swelling. That has an impact on the overall porosity, and we can see that there's something is changing in the pore structure, in the material. Then, well, I know I'll show you these graphs before you've actually presented the methods, but let's just make a brief introduction. This is mercury intrusion porosimetry. You have a sample which you have dried in a way, one way or the other. And then you press in mercury at increasing pressure. And assuming a given shape of the porosity, you can link this pressure, a given pressure, and the amount of intruded mercury to a relation between intruded volume and pore size. And this is the pore diameter we see here. And note that it's the smallest diameter here. So they start to press in at low pressure here, mercury, and at a certain time, some mercury will enter the pore structure. And what we see here is that depending on the way the material is dried, we get different values, we get different curves. Freeze drying, vacuum drying, drying in oven 60 degrees, and drying in oven at 105. And what you also see is that depending on the material, here we have a Sim 1, and here we have a Sim 5. It's two different types of cement. They have the method of drying has a different relative impact on the measured porosity. So this is something we need to consider, and well, first of all, you need to do it in a repeatable way when you're comparing, but you also need to consider how to do it to get the results which you can use. Is it insufficient drying, or do we actually damage the structure? Could be that we have chunks or stoppers or whatever you call of the liquid still in the structure which limits the ingress. But it could also be that we have damaged the structure. This is another technique, and this is data for low temperature calorimetry, where you have a sample, a saturated sample, and you subject it to cooling, and at a certain time there will be ice formation in the sample, and then you are measuring the heat development due to the ice formation. And the smaller the pores, the lower the temperature when you will see this heat development. So this is an indication of the pore structure. How it's described now is that when you start the freezing front will start from the outside, move inwards. So if you have very fine pores on the outside, the freezing front has to penetrate these. It will take some time. And then behind it could be that you have larger pores. So the freezing curve is a picture of the bottlenecks or the threshold pore sizes. Similar to what we see for mercury intrusion, we have to press the mercury into, and the first pore size where we have ingress, that would be the threshold, the bottleneck. For instance, if I have to freeze from here, I have to go through this small one before I can enter the larger one behind. Threshold pore sizes. So this is what we see. Then they had a so-called virgin sample, meaning a sample which has not been dried out. And this is the one you see here, and you see they can cool the sample quite long, or to low temperatures, before they see any freezing. If they dry the sample to 97% relative humidity and resaturate it and test it, they don't see much change in the peaks, neither to 92%, but then 83. We have a new peak here, as some of the structure has collapsed, and we actually have opened up the pore structure. And you can see the lower the relative humidity the sample has been resaturated to, dried out before it was resaturated, you have a larger and larger peak, indicating that something is happening. We're destroying the structure. So the size of the percolated pores, the interconnected pores, increases after drying and resaturation. Yeah.
Okay.
Please.
Yes, can one associate a pore size scale with the temperature scale?
Yes. Yeah, you have Gibbs-Thompson's equation where you can translate, making some assumptions again, that you can translate the temperature to a pore size. Yes. And that's done. Pardon me? Yeah. And the translation, or the Gibbs-Thompson's equation, at high temperatures, small changes in temperature has a huge impact on the predicted or the calculated pore size, whereas if we are having lower temperatures, it's more robust. Yeah. So this was drying. Just if we then, it could also dry with when we are by heating the sample. And you can see here that if we heat the sample, we have some of the phases in the system to start to decompose the gypsum. Well, for instance, if we were drying at 105, which we saw that was used for the data giving the background for Power's model, we can see that we have gypsum and yttringite starting to decompose, and also the CSH. And in addition, we may have some crack formation. Another thing you have to consider is carbonation, where you have carbon dioxide from the air, or possible carbon dioxide from the air, reacting with the calcium from the system. It could be from the calcium hydroxide, it could be from the CSH. And here you see the impact of storage on the measured surface with nitrogen absorption. And there's a coarsening of the structure. You see, if you just keep it there, your sample in a plastic vial, and this is a little more than a month, you have a change in, 40% or something in the surface area. So keep your sample in a way that they are not exposed to CO2. In much of the experimental work or the data you will read in the literature, a technique so-called Ddrying is used. And in Taylor's book, which is a very good book if you want to have information on cement and cement-based materials, it's described as you have the sample equilibrated at approximately -80 degrees, and you evacuate it continuously at a given partial water pressure. This Ddrying compares quite well to 105 degrees in CO2 free atmosphere and no control of the humidity, which is typically what you would do in a lab oven, or 105 when heating at a certain rate. There should be some information on the sample size also here, but I haven't written it down. And again here, we're talking about the water loss. It's defined as the evaporable water, and the remaining water is the non-evaporable water. And as you first saw before, it's not identical to the chemically bound water. And I'll just mention a method which has been used increasingly and in connection with the recent Mercury project and also with the core projects where we have liquid exchange. And here it's liquid exchange with isopropanol or isopropyl alcohol. So the method can be used both to stop hydration, which you may want, and to dry the sample. You can stop the hydration relatively rapidly, but if the sample is younger than 1 day, you should use another method, freeze drying. So the sample is cut into thin slices, 5 millimeter or less, and then you place it in alcohol, and you need an amount of alcohol 50 times more the water in the pores. And then after some time, some days, you take the sample and evacuate the alcohol, and then you can store them in. Of course, again, when you're storing your sample, you need to store it in a CO2-free atmosphere. The advantage is that it limits the development of microcrack. When you dry the sample with the alcohol, you set up less stresses, create less cracks. And then, well, if you want to stop hydration and dry a sample which is younger than 1 day, you need to use a method. And then you could have some problems of creating damages due to the cutting. Any questions? No. Okay, so we start on characterization of pore structure. If we have these two samples, could be that I say, well, how do I describe the differences between these? What would you say? What would you describe? Which properties? Or what would you like to describe? Total porosity? Maybe surface area of the solids? Pore size? Yeah. Could also be, yeah, topology. So, if we just talk about the porosity, it's total porosity, we could say. And often we would look at the moisture-filled porosity at a given humidity. That, for instance, if we want to determine the sorption isotherms. We could also be interested in the connected porosity or the percolated porosity. And especially if we're talking about ingress, that's of relevance. The surface area, to describe the amount of water absorbed on the surface. And it's also an indirect way of describing the fineness of the pores. The pore size distribution could be relevant. And then the tortuosity and the pore shape. And the tortuosity, it's defined as the twistedness or the distortion of the path. And we have this tortuosity factor, which is the distance of a molecule will have to travel to get through the sample, divided by the thickness of the sample. And I don't deal with that anymore, but you need to know the term. So the total porosity, let's have a look at that. We can use microscopy, and we can use volume or weight differences between filled and empty pores. And if we use microscopy, we can look at different levels. We can have visual appearance of impregnated planes, sections, large sections, optical microscopy of the thin sections, and then the scaling electron microscopy. And we can even go further down. So this is a plane section. That's a core which has been drilled out, and you can see it looks horrible. It is actually a core which has been, we've had alkali silica reactions, and there's an extensive cracking parallel to the surface. I find it very useful to start at the meso or macro level, because you can end up with looking at a very small place which is not representative and where you don't capture these macroscopic effects. So depending on what you actually need, which type of information, you should also look at the entire sample. And with this fluorescent technique, when you use the UV lights, you can see the cracks coming up so easily. It's the same technique with the impregnated samples we use for the thin sections, but here they are, as you can see, very thin, and we can look through them. And if you are to compare with standards, it's important that they have a given thickness. And this is this 20 microns, which is typically used. And I told you earlier that the thin section technique could be used for estimating the capillary porosity. And here you see some reference samples which have been prepared by a Danish company. And you can see the relationship between the green, the intensity, and then the water cement ratio, 0.3, 4, 0.5, 0.6. And it's a fairly good technique. And if you're trained comparing samples, you can and if the samples are homogeneous, you can do it with an accuracy of 0.2 or so. But of course, when you're doing this, it's apparent capillary porosity because the samples have to be cured in a similar manner, and so both temperature and time-wise. If you cure your sample for longer time, of course you will have an apparent lower capillary porosity. Then we can use the scanning electron microscope. And for porosity detection, we use the backscattered electrons. And as you saw similar to on Monday, they are detected from the upper layer, not the same volume as where we detect X-ray from. So here we have the sample, and it would be this area, or the volume where we have backscattered electrons. We can detect the backscattered electrons from. And this is, well, a little less than half a micron in width. The way it's done is that we look at this one first, where we have the gray level. And in this area where the dark, it will be the brightest materials, where we have the highest atomic number. And here we will have the porosity. So this will be the anhydrates, this will be typically the CSH, and then gradually it's coming the pores. And usually there's a threshold for the pores set by using the tangents for the two lines here. Let's see if I can show you. Ah, that one from the CSH and this one from the pore. Here you have a graph showing the comparison of volume fractions determined by backscattered electron or scanning electron microscopy and image analysis, and then methanol absorption. And that compares quite well. So the advantages of this method, well, it's direct, and it's reproducible, contrast from well-polished samples. Of course, you need to be sure that you're actually impregnating the porosity, and they need to be well-polished, the samples. Matters of consideration, that's, well, how do you actually determine the threshold, the gray level? And coming from 3-pore size distribution, well, you cannot determine it from 2D images. You have the impact of the sample preparation, and then you need a lot of samples or images so to have a reasonable accuracy of your data. And finally, depending on which type of porosity you want to detect or measure, you could have the problem with the haptic grains, because you also detect them as porosity. And here we have the definition of the Hadley grains, and we've already talked about those, so I'll skip that. Then the total porosity, the space filling, that would be the variation in volume, either because you press a volume in and you can measure the volume change, or the amount of material going into your sample, or you measure a weight change. And the material ingressing into your sample or entering into the sample, it will depend on the size of the molecules. If you use water or helium or nitrogen, they have different size, and they also have, if they are hydrophilic or hydrophobic, so it'll have a different interaction with the material. Then the method, you fill the sample with the method of saturation, and I'll come back to that in the next slide, and the method you use for emptying the sample will have an impact. The temperature you measure at, the sample size, are you actually able to penetrate the full sample? And again, how have you conditioned your sample before you start to do this test? And for the nitrogen, well, you have to have the water out before you can have the nitrogen to enter, and also for the helium. So you have to dry your samples in a way. The graph, I'll take that first. Illustration here, it's for bentonite. That's why we have this huge amount of water and desorption isotherm, which is quite different from what you see. We used bentonite to intermix with cement to decrease the clinker factor in some samples. So that's why and when we were mixing the bentonite in, we needed to know how much water would be absorbed in the bentonite and when would it be released during hydration, for instance. So that's why we did this. But it illustrates that if we are just having absorption, capillary condensation, we are able to fill the sample according to the black curve. Whereas if we apply suction and pressure, we can actually fill more of the pores, the larger pores. But we do not have condensation in the larger pores. So therefore, we need another technique. So the method you saturate your sample with, do you have capillary suction? Or do you actually use vacuum saturation, which is used in many of the standards? Or do you pressure saturation, where you will pressure the whole lot? Pressure saturation, well, the difference between capillary suction and pressure saturation is used in some standards to detect the air voids, the amount of air voids. The duration, if you're using capillary suction, the duration has an impact on the amount of water ingressing, especially if you have low water cement ratio or dense materials. And then you could have some problems as prolonged hydration. Well, when the water is entering, if the sample is not fully hydrated, it will keep on hydrating. So you're changing your microstructure during the conditioning. Leaching. Leaching is that you have dissolution, part of the solids in the material, and the ions are then going into the water. If you have a small sample, large amount of water, you can have leaching, especially of the alkalis. And that will change the material again. And then if you use a large pressure, you can have part of the porosity destroyed. And you end up with something which is different from what you wanted to look at. So, the next issue, connectivity.
Excuse me.
Yeah. Yeah, could you use this one?
Yeah. In a slide, you showed that you said that we cannot determine the 3D pore size distribution from the 2D images.
Yep.
But isn't that contradictory to what Karen said yesterday, that the volume of a phase change per unit is equal to the surface? I mean,
Yeah,
is that
you need to assume that you have isotropic, an isotropic structure, that it's similar in all in all directions.
Yeah, but
Yep.
you need to assume that to be able to calculate the 3D
Yep.
port
Yep.
distribution.
Yep.
And do you usually do that? I mean, is it acceptable as a hypothesis?
It's done. Yep. So as long as you state your assumptions, yes. Yep. Okay. So, percolation. Well, a continuous, that's the definition, that you have a continuous or percolated pathway of a given size throughout the sample. And it's caused by connected pores of a minimum size throughout the sample. So, and then in connection with that, it's also relevant to look at the ink bottle pores, where example B is the ink bottle pores, where we have from the exterior that we have a smaller pore size, and then it's going into a bigger pore size. And such ink bottle pores, well, it causes these characteristic pore sizes, or they are the characteristic pore sizes, and then they cause hysteresis. Difference in the behavior when drying and wetting. The methods we can use to determine the conductivity is the low temperature calorimetry. And here we have to consider that it's only the saturated porosity which is detected. It's the freezing of the water, if there's no water in the pores, nothing to detect. And then mercury intrusion porosimetry, and there's a lower pore size, typically 3 nanometer, but that depends on the pressure you're using. And we have to consider the conditioning of the samples in form of drying, and then there are working environmental issues. And I know that several have taken down their instruments because there were these issues of mercury. The low temperature calorimetry, it's not that much used, but as it can be used on virgin samples, not dried samples, it has a potential which we want to look more into, and it's part of, it will be used in connection with the product we're looking at. It provides information on characteristic pore sizes, and if the pore sizes are large, you have a difficulty of determining the pore size. So it's in, typically if you are to, it would be in the 2 to 40 nanometer range. The total porosity containing freezable water we'll have information on, and from the heating curve we can obtain pore size distribution, and again that would be the part of the porosity where we have freezable water. The principle is that the free energy of the water in the pores is lowered due to the size of the pores, and that induces a freezing point depression. We also have a freezing point depression due to ions in the pore solution, but it's less than what we see due to the pores. Here we have a pore. We may not draw it like that, but here we have a pore, and this part is the pore wall. Here we have the adsorbed water, and here we have the condensated water. The condensated water, we can, the size of the meniscus, we can obtain from this Gibbs-Thompson's equation, and here you have all the parameters, where we have the radius of the meniscus, the molecular mass, the surface energy, and the heat of fusion, and the temperature difference. The freezing point in bulk there, and the actual freezing point which we are measuring. And the layer, the thickness of the layer, that's a function of the temperature. So how do we measure? We place a sample in a calorimeter, and then the temperature is gradually lowered. We have a cooling, and we measure the heat flux. And at a certain temperature, the heating takes place, and we have a thawing of possible frozen water. And if we look at a sample here where we have pores, this is the water, and we have some freezing, takes place from the exterior, and we see the first peak. And at a lower temperature, the next part of the pore water will start to freeze, and finally the smallest pores are freezing. And then part of the pore water, which is not illustrated here, but if we have porosity here, it will not freeze at these temperatures. And here you see an example of some materials where you have reference. It's mortars, just an ordinary Portland cement mortar, where you can see the change in freezing curves of samples cured for 1 day, 7 days, and 75 days. And when you look at this, you can see here that at 1 day we have very little of the fine pored material, but it's increasing with time, whereas we see that initially we have a lot of water freezing at high temperature, whereas at 75 days nearly none. So we have got finer porosity and maybe many threshold pores. And when you're looking at you can see here the thawing curve, you can see it is development of threshold pore sizes, because there's such a difference between the cooling and the freezing curve. So this is what I said. So we have a refinement of the pore structure. The advantages of this method, that's that we can use virgin sample, non-dried samples. It doesn't take that long to freezing, so the samples can be fairly young. It takes 4 hours or so until they freeze. But of course, it depends on your cooling rate. We are at DTU using samples the size of my thumb, very large. Others are using much smaller samples, and they can have a more rapid cooling. There are several methods of consideration. When determining the heat flux, there might be a difference between temperature difference between the thermal pile, where you're measuring the temperature, and the sample. And if you have a lot of water which is freezing and the temperature is decreasing at a given rate, well, there will be a temperature lag. Then freezing, you may have supercooling of your water or the pore liquid, and often a nucleation agent is used to ensure that you don't have that much supercooling. There might be migration of water from the interior of the sample out to the surface, so freeze drying. We have to consider the ink bottle effect, which is not considered in all literature if you go back. We have the freezing point depression due to the ions, and when the freezing takes place, you have a brine being made. So the water is freezing, but the ions are being left in a part of the solution which is getting more and more concentrated. So we have this accumulation of ions in non-frozen pore solution, and then there might be possible cracking. So you see, it's not perfect. Then thawing, possible damage of the material, inhomogeneity of the pore solution, which we get, and we have the phase change transformation. Then when we are calculating the ice formation, there's a discussion of which value of the heat of fusion to use and which surface tension, value of the surface tension to use. That also has an impact on the calculated pore sizes. Here you have a curve showing the impact of freezing rate on the freezing peak, and this is just water in the calorimeter, and we are freezing at low rates, which gives a distinct peak whereas if we are freezing at high rate, we have this flat peak, which you can see here. And the same for the thawing curve. If we then add ions, we see a change in the peaks. It's just a very simple system. We wanted to see what was happening. So we have this. We have the phase diagram for sodium chloride, and we have a 10% solution. So we cool it, and get to this value where we have some of the water will freeze, and we have an increasing concentration in the solution. And we can see that we have this first freezing of the water here, and then we have the phase transformation around, well, it should be around minus 21, it's a little lower. If then we have a system where we have pores and ions, we have the bulk liquid freezing, we have the sodium chloride in the bulk, and we have initial freezing in the pores, and we have the salt in the pores. And then you can imagine, then this is just one pore size. Then we have the system, our cementitious material, where we have a variation in pore sizes, and we have several different ions in solution, and the concentration changes. And we don't have a phase diagram for the pore liquid.